Okay, thank you, Murad. And good morning, everybody. I'd like to thank Intel for making available this spectacular venue. And I think this will be, as all the previous NICE conferences, a very, very good one. And we have developed a good style in this conference, I think, over the last 6 years, that there is a lot of communication between the speakers and the audience, and there are these open mic sessions, and I would all encourage you to really contribute to that. I think this is a unique opportunity to bring together many, many fields, like, by the way, we do in the Human Brain Project. And I'm supposed to say a few words on the Human Brain Project. I'm representing, and I say this every year, a funding agency, but I am not a funding agency. I'm profiting from a funding agency. So in a way, I'm the wrong person to do this. But in any case, I would shortly introduce the Human Brain Project and then, of course, say a little bit on how we do neuromorphic computing there. The Human Brain Project is really a combination of basic science, of neuroscience, and you see the neuroscience block here, from experimental neuroscience to cognitive neuroscience and also theory in particular, which is very strong. And it is linked through a process that we call co-design, for building what we call platforms that are computer-based infrastructures that we hope can contribute to improve our knowledge of the brain, but also do the other way, go from this neuroscience knowledge and build computing infrastructures that are used outside neuroscience. So there are these 6 platforms. I have no time to go into details, but of course there is one which is called Neuromorphic. This is what I'm going to focus on. And the goal of this is to produce, as I said, knowledge about the brain. That's the basic science aspect, and applications in brain technology, which in the European language is called the innovation aspect. Now, this important thing is that these platforms are open, so they can be used by people outside the project, people outside Europe, so by you, for example, and I will give you some examples on how this is being done. So you know this, of course, we have seen that before in the introduction. Why would you do this? There are 2 reasons. One is to learn about the brain. The other one is to transfer biological principles that we find in the brain to generic computing devices. And whatever you do, you always need model systems to test your ideas. You cannot just think and say it's like that, but you really have to test your ideas with model systems. And in HPP and in many other places, we feel that there are 2 ways to do this. One is what we call a numerical approach, where you represent the quantities that you find in brain cells and brain networks by binary numbers, and then do numerical computation on them, solving differential equations, for example. The other one is what we call a physical model, where the biological quantities are represented by the same quantities also on the synthetic substrates. The voltages are represented by voltages and charges by charges, and so on. And in reality, of course, it will always be so that you do both at the same time and build what we call hybrid systems. So this is the HPP neuromorphic computing strategy, and we exactly follow the 2 ways I just mentioned. One is the sort of the numerical modeling approach. In this case, a many-core system based on many, many ARM processors. This is the Spinnaker project, which has been conceived around 2005 or so long before the Human Brain Project really started. But in the Human Brain Project, it's now well integrated into this framework, which I just showed. The second approach is what's called brain scales. It is a physical model, so it's partly analog computing. There is local analog computation, but like in the brain, binary continuous time communication. And as a first step, based on previous project, we built these relatively large machines, which you see on the top there. There is the Spinnaker machine with currently 0.5, soon 1 million ARM cores. That is a real-time simulator, and it is available remotely. The second one is located, Spinnaker is located in Manchester. BrainScales is located in Heidelberg. You see it looks similar. It's a couple of racks with lots of electronics, but it's fundamentally different in the sense that it is really a physical model with several million neurons and a billion plastic synapses. And it is an accelerated system where time is compressed, in this case, by a factor 10,000, which shows a lot of advantages for learning, for example. Now, within the Human Brain Project, the important thing we feel is that we use what neuroscientists tell us about their latest knowledge, and we transfer this to the next generation. And that's what we really do at the moment. And at this conference, we will introduce the two 2 new prototype chips for Spinnaker and for brain scales, which for Spinnaker is now having like more than 100 ARM Cortex cores per chip, 36 giga instructions per second per watt per chip. So that's typically a factor 10 of computational performance with constant power. Brain Scales has made a step to put more neuroscience on the system, and that is really mostly dedicated to the ability to learn and to learn locally. There is now, diverting a little bit from the pure neuromorphic idea, there is an on-chip processor, a programmable processor that can do local learning. It can influence the network structure and the network features, and it can do what we call flexible hybrid plasticity, because hybrid means it's a programmable processor and then this kind of mixed signal network. And in addition, there is a new development, which is that neurons now on brain scales are far more complex, at least if you wish so, than they have been in the past, where we had only point neurons. Now there are active dendrites with calcium and NMDA plateau potentials, which should offer interesting possibilities to do learning, which is no longer software-based, but really based on the neuronal activity in particular in these dendritic structures. Now, in addition to building hardware, which is a lot of work, there is also a common software ecosystem, which is important so that everybody can use these platforms. It offers remote access, and it is an open user facility. And the fact that all this work, there's a word missing here, there's a very close collaboration with theoretical neuroscience, which really drives the design of these new machines. And at this conference, all the key people are here, actually. So there's Steve Ferber for Spinnaker. Sebastian Schmidt will talk about the use of the large-scale brain scales machine. And for the next generation, Sebastian Höppner on the Spinnaker 2 prototype, and Johannes Schemmel on the brain scales, a new prototype, and there will also be demos, for example, presented by Eric Müller, also by Sebastian. And from theory, Wolfgang Maas is here, who has always been one of the drivers of these new designs. Before I close my short contribution here, let me show you some plots which I find quite nice. This is sort of the usage, the job submission in this particular case for the brain scales machine, is starting in May 2016 when the thing was first made available. And you see this is a cumulative plot, I have to say. There's a constant rise, which is a good sign. So these are the sort of the old-fashioned machines, if I may say like that have been conceived around 2005 and which are now in a stage that you can really run experiments. There's a funny thing which you see that these new chips that we built, this is particular, again, the one of brain scales with the plasticity processor and the active dendrites. You see also there is some kind of uptake. People start to use it, and very recently it just shoots up because people have discovered that there is interesting things you can do that you couldn't do with the previous system. For Spinnaker, I'll show you this, which is very nice. There is a map of the world, as you easily see, and the blue locations are the ones where Spinnaker machines, actually little machines, not big machines, are located at this moment in time. And that's is quite impressive. It really means that we make neuromorphic computing available to a big community, and we hope to contribute to develop the field. I will make a little bit of propaganda for my own case here. In Heidelberg, we have recently been breaking the ground for a new institute, a European Institute for Neuromorphic Computing, where we hope to build future large-scale machines, and it should be a focus point really for this kind of research. And if you're interested to contribute, of course, you're all very welcome. If you want to know more about neuromorphic computing in the HPP, of course, there is a website, neuromorphic.eu, and there is what we call a guidebook where people can really read what the systems are like and also get instructions on how to use them. And that's all I have to say for my short introduction. Thank you very much.
So thank you very much. It's great to be here. I see so many familiar faces and so many friends that it's just fun to see everybody. So I'm from DARPA, and my non-DARPA computer is saving us. Perfect. What I would like to talk is about one particular program, which is lifelong learning machines. There are many relations between this program and what Karl-Heinz was talking about, but we're not going from the direction of simulating the brain, although this is 50% of what we actually do, looking at the biology, while the other 50% is building systems. But we come from different direction. So the different direction that we come is to ask what we miss in AI, and then what we miss, how perhaps we can try to get it. So the thing that we miss in AI is not the capability to play games, is not to work on images that are well defined in advance. The issue is to have system work in the real world. And why is it a problem? I think that the New York Times said it very well, that when you have this kind of self-driving cars, and it does not have to be cars, it can be any automatic systems, you have this issue that the system cannot be relied upon to react in every time, in every situation. That means that if you drive a car and there is a 24-year-old driver in the same street, then maybe the car cannot drive. Or if there is a drunk driver in the same street, maybe you yourself know what to do, but the car does not. So the issue that is, whenever you look at all these type of accidents, so legally they always find that the cars and the autonomous systems were doing totally fine. And the question is why? The real issue is that these systems cannot do things that they were not trained upon, because the current machine learning that we're talking about is really not as much machine learning, is much more machine training, which means that we have to train the system. And if we didn't think about every eventuality by the time we train the system, when it's going up to react in the real world, it has a problem. So one of the real reasons that, coming from the field of neural networks, one of the real reasons that in neural networks we're not talking about lifelong learning machines is that in neural networks, you have to start with trained data. And when you train the network, then you have a fixed neural network, and then you can operate. Now, what's happening if, let's say, the car sees something that it was not used to? So if it tries on the spot to take this data and try to train on that, you know what will happen if you are in the neural network world. The weights of the network will all change. They will bias towards this new situation, and they may forget the many million other situations that we trained them before. We don't even know which of them they forget and which of them they don't forget, because we actually wrote over the whole memory. So this is not really working. And the question is how we're able to do that and why it's so important. The reason that it's very important is, first of all, to the DoD, but I think it's important really for all of us. So the main way that we want to think about it is that the orange line is the current type of machine learning. So if you look at the left, assume that we don't have millions of examples because we're not Facebook or Google, and perhaps our examples are examples from the physical world and not examples that are easily coming in images or in cyber data. In that case, we really have to collect intelligence and put it in the system, and we would like to fill the system at some point. If we're working with a system that is frozen during its lifetime, it will stay constant with its performance. If we allow it to improve from its experience, kind of like any animal, it will improve over time. But the right side is even more interesting. So on the right side, we have this issue that we can train on data from Afghanistan and then fill the system in Syria. And you know, from far away from here, these two countries seem kind of similar, but when you go to the details and to the details that are being used, it's possible that the system that we train on was kind of a good approximation, but it's not really working in reality. What will happen in current neural network, if you don't know what to do, if you're not trained for, then the network will give you default. This is what we see in the orange line that goes down. So the system will stay in default even if the person or every person that will see it, we'll see that it's constantly give you the default, it's constantly not prepared for the situation. While what we want to have in lifelong learning, or what we start working for, because as I'll tell you, the program is really starting already, we would like to realize, the system itself, to realize that it doesn't work as well, and to be able to open its own training while really asking a very hard question of how to do it, but do it without forgetting the previous information. I would like just to go forward for a moment, just to talk about some properties that we really want to have in lifelong learning systems. So these are the 5 core capabilities of the DARPA program. The first of them is continual learning. The system is capable of learning during execution without forgetting the previous data. The second one is adaptation to new tasks and circumstances. We would like it to be able to apply previous learned skills and use them without being told exactly how to do it. There is a very hard issue, which is how we choose our own training data. So in classical network and classical AI, we're giving training data. It can be labeled, it can be unlabeled, it can be with reinforcement learning, it doesn't matter. But somebody already prepared to us the training set that they told us that that's what we have to know. Now, us, in reality, how do we choose what the training set is? If I want to recognize a face of a person, how do I choose which light, which details, which features? How does it work? So this is the third part, which is goal-driven perception. What do we take from the environment? How do we create online our own training data? The reason that we call it goal-driven perception is kind of like a hint from biology of how we think perhaps this should be done. So if I'm searching for a person, I may not look at the different cars or the different pictures on the wall. So that's the goal-driven perception. Selective plasticity is a hard problem that we're dealing with, and we take some ideas from biology. The idea is that if you have a system that all the time changes with input, then it does not keep a memory stable. It's not really learning and memory system. It's just kind of a mirror. On the other hand, if you have a system that is too stick and not changing, then it's not an adaptive system. Something in between is perhaps the other. And safety and monitoring, the last one, so people that work with animals understand where safety is and how we have predictive models and what healthy animal and people do before they react. We would like something of similar case to here. So I want to go back for a moment and give 5 minutes of the why we think we can have it. Actually, we start having it, but what we need to do in order to be able to change the way we think. So I think that the way we think in computer science still, even that we know differently, it's very ingrained in the way that we teach our students, is this great model from 1936, where the idea is that we have a universal computer. We have a program, a loadable program. So the program is written in advance. Then we load it to the computer. The program does not change. And when the program is in, we're able to act with it on input and output. That's great. So what we do in AI, if we use that kind of system, one way is that we can write program and rule-based systems. This is the loadable program. You can load it and have an AI working. Another way that we can think about it is what we call parameter learning, or what is called machine learning. Is, let's say it's a neural network. We load a particular neural network. We load also a training set. And then we do kind of something interesting after the loadable program. We take the neural network with the loaded training rule, let's say backpropagation, and the data set, let's say ImageNet of CFAR10, and we train the network on this thing. Once we finish it, we load this network. From now on, it's frozen to the computer and ask the computer to work. So if you want to think about it, what we do in machine learning is kind of similar to the loadable program. This is the network, the training rule, the training set. Then we take this little white area in between the loadable program and the computer and do another step, which is the training set. And then we have a frozen program. We put it there and we go forward. So this is not exactly how we people work. We're not trained all the way until second grade, and then we're being frozen. I mean, the whole idea is to learn with experience. So in biology, this is a no-brainer. You know, we don't have to convince anybody, and everybody that work with biological system understand that there is really nothing to talk about it. Brain reconsolidation is all about having memory active, retrieve memory, lose that memory, and reconsolidate it again when it's never the same. So the memory that is all the time changes, the epigenetic, the genetic may be fixed, but the epigenetic is changing. So these are but two examples of how biology thought to allow us to have systems, let's say DNA, but all kinds of other things that allow us to change how the system works. In terms of computer science, we also have a theory for that, and we know that there is a whole class of computation, which is the super Turing computation, and there are different ways to consider how we move from the Turing machine, from the super Turing machine. In reality, there is a continuum hierarchy that goes from what is Turing computable to what is super Turing computable. Because super Turing computable is a very particular class, and it's not tautology, it's not everything. So I'm putting here a possible ingredients, and mathematically all of them are equal. If we move from discrete variable to analog or physical variable, we jumped all the way from Turing to super Turing, or if our values are somewhere in between digital and analog, which we can discuss about it, kind of computable real numbers, then we have things along. Another way that can take us out of the Turing regime is to have some randomness that can be either by a coin or by asynchronicity of parts. And if this coin is not exactly half and half, kind of promised from God, but is actually some real probability, or if the asynchronous is kind of natural asynchronicity of a system, we're already in the super Turing. But the interesting part for this program is that if we move from the pre-program all the way to the plasticity or to the evolving system, a system that can change based on its input, based on its environment, we are, even in a very, very simplistic way, we already jump all the way to the super Turing computation. And another interesting part is if we talk about systems that do not stop working, it's not question answer, but system that has unbounded input and continue to give output. By moving from Turing to super Turing, we're going from Aleph 0 different functions to 2 to the Aleph 0 different binary function. This is a huge difference. So the interesting part is that Turing, in fact, was the first person that talked about computing beyond the Turing limit. So it's not me, it's Turing. And he actually explained that what we call Turing machine is there to work in discipline by unintelligent matter. He put 4 years of his life to talk about machines that will work like the human minds. The very interesting point is that while I didn't know about it, once I learned Turing came with exactly the same 5 principles. When I asked from theoretical computer science, he asked how can we get artificial intelligence? And he came with exactly 5 principles. You know, he died a little bit before it was completed. There is one point to say is that when we're moving from system that changes, or super Turing, and system that is fixed from Turing, we didn't really reject the previous model. We actually encapsulated the previous model as a sub-part of that. So if you think about the brain or any system, at every time it's run an algorithm. So at every time it's a Turing system. But with the adaptation in between, at every point of time, if you look, we are running a different algorithm. So today I'm running a different algorithm than tomorrow, after what I hear here, but I'm still running. So we have Turing machine at every point, and the whole thing together is the super Turing. So I'll finish with this slide. Actually, with the next one. So I want 2 more. So the idea is to move from the rigid model to the flexible model of continuous adaptation. And just kind of to give this one, which is usually I'm not showing to the crowd, but since this is a very particular crowd, I want to say that we have 2 technical areas. One that builds the system, and the other one that is going to the biological system. brain and others. We have actually 2 people here that the grants were already approved, but they don't know it. They will have to wait next week to hear about it. Most of our people are under contract. And what these people are asking is what particular property in the biological system that look give this property of lifelong learning. How does it work that we don't forget things that we learn new one? How can we take the new information and consolidate it in such a way that it's really a natural part of everything? How can we keep safety and security even that the system modifies all the time? So we ask very particular questions. We don't ask, give me a brain and copy it. We say, what are particular issues that will give me lifelong learning? And with this, I want to thank you very much for inviting me.
All right, thanks. In the next few minutes, what I'd like to do is talk about the new center that we have, the Center for Brain-Inspired Computing. That center is actually funded by SRC JUMP. JUMP stands for Joint University Microelectronics Program. There are several industries associated with it, including Intel, IBM, Micron, and outside of the US, TSMC, Samsung, ARM, and several of the defense companies like Raytheon, and so on. So, and of course, I forgot to mention, DARPA is putting in about 40% of the funding. So DARPA and these SRC companies. We got started at the beginning of the year, and what I'd like to sort of briefly talk about is the kind of things that we plan to do. We are already in an AI-centric world today. Today we use AI applications, web-based searches, recognition, and so on. But there aren't really too many killer applications that we have today. Turns out that if you're really talking about self-driving cars or personal robotic assistants and so on, you would have to go beyond what today's AI is, going into autonomous intelligence, where the computers probably have to perceive things around them, reason about it, and take an action or make a decision and take an action on that. And that's quite a challenging task. Once you go from, for example, the current systems, which are really perception-centric, which are usually good for search, speech and image recognition, natural language processing, to future systems where you need to do perception, reasoning, decision-making, and possibly not just on the standard CMOS devices. There are several interesting neuromimetic devices that are coming up, and the possibility of actually combining deeply scaled CMOS with these emerging devices can potentially give you a large improvement in from a quantum leap from today's systems. But there are several challenges. There's a radical growth in the computing workload, which is sort of unsustainable. A lot of these applications that we've been looking at are, for example, self-flying drones or self-driving cars. They're safety-critical applications. There's a need for actually having theoretical analysis on some of these problems to be able to actually calculate the robustness of the system. And a lot of these systems, when they're developed, they know how to behave when they're seeing inputs that they have seen before. But how do the systems behave when they haven't really seen inputs that they haven't seen earlier? There's a diverse application space. Can we actually play with small and dynamic data? Can we learn with lot less data? Today's model building do take a lot of time. The question, of course, is can we really come up with new methodologies of learning where we can learn with much less data? And most of the intelligence today is cloud-based intelligence, and that may not scale. And there's a need for actually having systems where you are going to have intelligence and learning on the edge devices, and you have to break it up into some sort of distributed intelligence between the cloud and the edge devices. So the vision of our center is to narrow the orders of magnitude computing efficiency gap that's there today between today's computing systems and the brain. There are several examples of it, and there are several examples of the computers or the AI systems doing much better than the brain, but certainly at what cost? We know that the AlphaGo beat the go master. But question, of course, is at what cost? There was possibly about a 10 to the 3 to 10 to the 4 energy efficiency gap between the brain and these systems. Can we drive improvements in the robustness of the cognitive computing systems? And as I mentioned earlier, that there's a need for developing more underpinning of theoretical underpinning of these systems. We will actually explore distributed intelligence across the edge, hub, cloud, and peer-to-peer networks. And peer-to-peer networks, that we'll see, is also going to be quite important when it comes to swarm of drones and that kind of intelligence that we're talking about. And finally, we demonstrate the impact of these advances in end-to-end systems for autonomous drones and personal robotic assistants. So what we have done is we have the organization of the CBRIC is in terms of different themes. The theme 1 is on neuro-inspired algorithms and theory. I'll briefly talk about some of these. And theme 2 is on neuromorphic fabrics. Turns out, and I'll talk a little bit about it a little bit later on, is the fact that whatever little that we know of the brain, the computing architecture is certainly not like a von Neumann machine. It's more distributed. In fact, in a lot of ways, the computing is done within the memory itself. The question, of course, is can we take advantage of some of the new developments in architecture and circuits and devices and build systems that are actually quite suitable for the neuromorphic algorithms. And finally, theme 3 is going to be on distributed intelligence. As I mentioned, how do we distribute intelligence and inferencing between the edge, hub, and cloud? And finally, theme 4 on application drivers, which are self-flying drones and personal robotic assistants. Now, one of the tenets that we'll be using is brain-inspired computing. And however, it's quite important to understand that we are at a stage when we were initially learning how to fly. It was certainly important to understand or important to know the principles of how the birds did fly. But today's 747s, which can go across the world in halfway across the world in 15 hours, do not flap their wing, carry certainly a payload of 400 or so passengers or so. Now, so from that angle, the question, of course, that comes up is what should be really brain-inspired? Are we actually use spiking leaky integrate and fire neurons, or should we really use other kinds of neuronal models? Should the learning be supervised, unsupervised? Should we use variations of spike timing dependent plasticity learning? What kind of network topologies are we going to be using? Should we have long-range connections, feedbacks, recurrent neural networks? Should it be like liquid state machines? And the kind of computing principles. Should it be asynchronous and event-driven? And what kind of input coding that we end up using? And those are actually the questions. Hopefully, we'll be able to dig into and answer some of those as a part of our research. Now, I'll briefly go into some of these themes. On the neuro-inspired algorithm side, and on the left side, I'm showing really the state of the art. What we feel is that it's going to be important to really look at the future neuro-inspired algorithms, which are has to be computationally efficient algorithms. As I mentioned earlier, there is very little on the theory of some of these deep learning or the emerging models of learning today. So there's a need for really developing underlying neural computing models and theory behind it. As Hava mentioned earlier, there was incremental and lifelong learning turns out to be quite important because today's systems they go through something called catastrophic forgetting. If you have learned, for example, a particular data set, and then we like to learn something else, some other data set, you have to relearn data set 1 and the data set 2 together. And that's quite inefficient. Is it possible that we actually do incremental and lifelong learning? It turns out that the brains, the neurons in the brain do show stochasticity, and there's a whole bunch of work which is going on coming up with new stochastic devices. The question, of course, is can we have the algorithms that can leverage stochasticity and approximate computations? So just to give you some examples of it on the theoretical understanding of learning, there's been work has started in earnest in these areas. It turns out that the random matrix theory and the principal component analysis and the eigenvalue spectral can potentially give you some idea about how learning is being done and how one can potentially, there's a lot more work to be done, or how potentially one can actually try to compare different learning methodologies. And on the other side of things, Hava talked about learning to learn, and it's important that we talk about lifelong learning. But is it possible? I mean, while we end up learning under a constrained environment where you have amount of memory to be constrained, it turns out that forgetting also is important. How do you forget? Is there a way can I learn to forget in some ways? While we learn to learn, is it possible that you learn to forget? And just to give you an example of it, I mean, the standard taking a small network with STDP learning, and if you actually do learn digit 0 first, followed by digit 1, followed by digit 2, what you end up seeing is that you probably haven't really learned much at the end of it. And this is basically a little bit larger new network showing the MNIST data set where, if you do such sequential learning, turns out that you may not actually end up learning a whole lot. However, if you actually have adaptive synaptic decay, turns out that you can change your learning algorithm and similar kind of input data. If you see digit 0 first followed by digit 1, you end up seeing that actually you end up learning digit 1 and digit 0. However, I mean, this is a very small network. Now, if I want to learn 2, it turns out that I have forgotten actually digit 0, which was in this particular case not an old data and possibly a not so important data. So the question, of course, is can we really bring in learning to learn along with the fact that there's a learning to forget under a constrained memory environment. Now, a few other things also turns out to be quite important are, when we look at different kinds of inferencing and networks, turns out that some inputs are easy, some inputs are more difficult. And so the question, of course, is can we really come up with mechanisms of variable effort or conditional deep learning networks where the things which are easy can be done quickly, things which are more difficult might take a little bit longer time. So can we develop algorithms and the architecture suitable for that? And that can potentially lead to lower energy consumption. Finally, on the other side of things, as I mentioned, stochasticity turns out to be important. And if I really look at, for example, probabilistic inferencing, or in fact, even the spiking neural networks, noise certainly helps, and stochasticity can bring in, not only, in some cases, better inferencing, but at the same time, it turns out that it can actually do, better memory compression. So just to give you an example of it, turns out that if you really look at spike time independent plasticity, and if you look at the learning mechanism, rather than actually updating the weights as a t pre minus t post to be some delta w, can it be associated with the probability of switching of a particular device? And if you do that, it turns out you can actually do binary neural networks. And if you have a little bit larger size of the network, it turns out that you can actually have really less complex hardware to do these things. And the underlying enabling technology certainly can be CMOS, which would require more devices, but it's also possible to have other kinds of new emerging technologies. On theme 2, we'll be looking at neuromorphic fabrics, both CMOS and post-CMOS technologies. And one of the important things that I mentioned earlier is that, computing in memory turns out to be quite important. And if I really look at today's, GPUs, the main memory consumption for these neuromorphic computing systems are really the memory. Almost about 70 to 80% power consumption is due to memory traffic and power consumption in the memory. So is it possible that I do actually computing in the memory itself? And to that effect, actually, there are different possibilities. I'm not going to go into any details of it, but it turns out there are possibilities of having computing memory with CMOS, certainly not with the standard 60 cells because there are some issues with that, but you can actually turn on a couple of word lines simultaneously, and you can do XOR operations, you can do add operations, and so on in the memory itself in a 8T cell or a modified 8T cell. Similar things are possible also in the post-CMOS technology with STT devices. And in other words, what I'm really showing here is that rather than having a conventional computing where you have loads and then at the end of it addition and stores, rather than that you can have a single in-memory computing operation that can potentially do these add operation and can give you large improvement. There are other possibilities. It's possible to embed ROM into a RAM directly. And you can do certainly different kinds of computations in the ROM itself as a lookup table, having different neuronal functionality, and so on. And that can, again, potentially give you a large improvement. And again, the ROM comes at no extra cost. It's actually a zero cost, and it can be done both in the CMOS and in STT kind of memory devices. Finally, on the distributed intelligence side, we'll be looking at partitioned algorithm and inferencing, as I mentioned earlier, between the edge hub cloud and peer-to-peer networks. Cognition and compressed data under such situation turns out to be quite important. And we'll be also looking at in-sensor analytics, which really requires that we actually develop very low complexity algorithms and hardware to enable that. And there's several examples of it where you can do actually, embed intelligence into your edge devices and the cloud. In this particular case, showing actually an example of a conditional deep learning with basically getting input from, physiological sensor data from the body and doing some on-body analytics. And if it's too complex, then you actually end up sending it over to the cloud. We'll be also looking at multi-sensor cognition, which would require, fusion networks. And in this example, showing an optical and an IR camera working together into a fusion network. And finally, the application drivers that we'll be looking at are the personal robotic assistants and the drones. The CBRIC universities, I just wanted to mention quickly, it includes Portland State University, and in fact, we have Dan Hammerstrom here, who's going to be leading the Theme 1 activities. University of Southern California, Arizona State, Georgia Tech, Purdue, of course, University of Pennsylvania, Princeton University, Penn State, and MIT. And these are actually the different, the organization of CBRIC and the different faculty. There we have actually 17 faculty as a part of our program, and I'd be more than happy to talk about to the PIs. Thank you very much.
So maybe just to get the conversation started here and then drawing maybe one or two more questions. The centers that are being set up both in Europe and US worldwide are quite extensive. So just wanted to get maybe a word or two from the panelists to see how they see potential collaboration or interaction among those centers. So I'll go ahead and start with Karl-Heinz.
Well, as I said, the HPP approach is to be open to external users, and they would certainly be interested to collaborate with CBRIC, and I'm very impressed by what you do. It's, what we have to offer, I think, is indeed a platform which is very concrete in terms of availability of hardware, which I think has some pretty unique features. And so I guess we should probably talk about collaboration. So I'm very open, definitely.
Terry Zinovsky. So I'd like to address one of the comments that you made about birds. So this is a criticism actually that goes way back to the 1980s, and here's how it goes. It says, if you want to learn how to fly, it's a waste of time looking at birds, at nature. Why? Because they flap their wings, and you're not going to go from New York to Los Angeles flapping your wings. Ha ha ha. I haven't finished. I recently read a book by McCulloch, which was the history of the Wright brothers, a biography. And it turns out they spent a lot of time looking at birds that were gliding. And from this, they were inspired to develop the first airplane that we all know grew into the 747. So the real take-home message here is that when you look at a bird, when you look at nature, you have to take away principles, not details. And I think it's time to put this canard away.
I think all of us want to say something about it. So this is something that I'm kind of faced usually with government, that they're asking why things have to be bio-inspired, and I'm totally like you. It's very clear that when you have all these feathers, you can also fly and then stop in the middle of the air and do all kind of trick. It's a very highly complicated, complex system. And perhaps if we can do more like that, we'll do better. But given that we have different kind of a material, it's possible that we'll just take some ideas. And I think in L2M, that's what we try to do, to take this notion of how biology does it and translate it immediately to what we can do. So I just kind of, okay, just before I go forward, it's kind of half related and half is something that I wanted to say to the previous question. We have upcoming few programs after L2M that are in the process. So one is a lifelong learning processor, which is the hardware program, where we want not only to be modified architectures, but modifiable, self-modifiable architecture based on what we need. We have adversarial machine learning, which is really safety and security of these systems that are changing. Again, a lot will be taken from biology, but also from cryptography, mathematics, and we want to take it and to incorporate in hardware. And the last one, which will be related to lifelong learning, will be a particular application for chemical sensors that will build on the notion of learning over time, because these are chemical sensors that you either implant in a body or put somewhere and you want them to continue. But let me pass it to you.
Yeah, thanks, Ava. That's a very important question, and in fact, to tell you the truth, our center is brain-inspired computing. And in fact, it's very important to understand that in fact, what I'm saying is that we need to understand, absolutely, while we need to understand how to fly, we certainly need to understand how the brain works. And that's why I'm talking about, should it really be a spiking neuron? Should it be a leaky integrated and fire neuron? Should it really be, spike timing dependent plasticity learning, which are sort of observed, sort of the hippocampus of rats and so on. So the question, of course, is the fact that, no, we will be exploring all those possibilities. And our tenet is really brain-inspired computing. And no, if I did mention the fact that we will not be, sometimes we do get criticized because we are looking too much on spiking neural networks. Absolutely not, absolutely not. Our focus is certainly going to be on brain-inspired computing. And if I did give you this impression, no, I didn't really mean it in any way. But what I really want to make sure that we do look at different kinds of applications, and some things are bio-inspired, and some things are going to be possibly, mathematical representations of some other ways of solving the problem.
Okay. I can only underline which was just said. It's, the principle of flight is exactly the same for birds and planes. It's the dynamic lift, which comes, of course, by moving the air across the wings. And in the same way, in brain-derived computing, we have to focus on the principles. That's very important. There are probably a lot of what we could call biological overheads, but there are principles which are yet to be discovered. But we have already discovered quite a few. Even a plain, simple artificial neural network that's used today for so-called deep learning is biologically derived. There is a biological principle, which is the structural organization of the brain. It's clear that the temporal organization of the brain also carries a lot of interesting principles, but those principles we have to find. And this is why I argue so strongly, also in particular in the Human Brain Project, for an extremely close collaboration with theoretical and mathematical neuroscience that can help us to find the more abstract principles, which we then is worthwhile to be implemented in neuromorphic architectures. But there is somebody who knows about flying.
Yes. So I'm Winfried Wilge from IBM. I'm also a commercial pilot, and so I have thought about the subject quite a bit. And thank you so much for saying that. If you want to build any flying machine, you have to solve 4 principles: lift, propulsion, stability, and control. The latter 2 are the harder ones, by the way. And the Wright brothers took 3 of these 4 when we built the flying machines, anything but the propulsion. So yes, we owe a lot from the biological insights in birds, absolutely. No question about it. It's a total canard, this argument.
So let's thank our panelists again. We'll have a later discussion session starting at 4:30. We can again pick up on these topics and then expand further, and that usually ends up being a very, very exciting time to bring those up. So let's thank our panelists again.